So in the main section of videos, I've got an example of how you can go about filtering an audio file. The example I gave is an audio file. It's a way you can filter any data, however. Now, that example was given using a lot of syntax coming from Mathematica, and I thought, in case people are more familiar with Python, I could run through how you would do the same example using Python. So here's a Python notebook that I'll make available online if you want to play with it, and we begin by importing a whole bunch of things from SciPy and NumPy that we need. So that's just the import part. And now we get to the part that involves audio files. So I've got an audio file here called noisyclaps.wave, and so I can import that. Of course, if you're doing this yourself, the path will vary. And I'm using this reading command here that reads a wave file, and the outputs are audio in and sample rate. The sample rate is the number of samples per second, so in hertz, and the audio in is just an array of numbers that correspond to the amplitude of the audio sampled at each point in the time space, so sampled at the sample rate. So I'll read that in, and then I've got a command here to play the audio at the correct sample rate, and we can listen to it. So we've got some clapping, some shouting, and a horrible high-pitched scream that covers the whole thing. And the goal here is to try and remove that high-pitched scream. So to begin, we need to define a whole bunch of things that we need for our Fourier analysis of the system. We'll start by defining the Nyquist frequency, which is half of the sampling rate. And we'll also find out the number of points of data that we have. So we know we're sampling at the sampling rate. We don't know exactly how long the data file is, but we can find the total number of points, and that's given by this command here. So this is zeros selecting along the correct dimension of this array. And then we know that the total number of points must be the total time of the audio file must be the number of points divided by the sampling rate. So we can define a vector of time data using the linspace command from 0 up to the total time, which is the number of points divided by the sampling rate. And the number of points we have in this vector is just the number of points that we've got in our audio file. So this is the time axis, if you like, that goes along with the amplitude in this array here. The frequency axis is going to be given by the a vector that goes from negative Nyquist frequency to positive Nyquist frequency, and it'll have the same number of points in that array. So this is our frequency axis here for when we take the Fourier transform. This is how we take the Fourier transform. We use this f of t command here of the audio input, and then we're going to call the Fourier transform data f of t audio in. So that's the fast Fourier transform of the input audio data. Okay, now we can plot our data in time and frequency domain and see how things look. So this first plot here is just the amplitude as a function of time. The second plot here is the spectrum, and the third plot here is just a zoom up on the spectrum around 6,500 Hertz, and we'll see why in a moment. The other command I've used here, which I should point out, is a command called FFT shift. Now, if you recall that the fast Fourier transform produces a vector of data in frequency space that starts at 0, goes up to the positive Nyquist frequency, then in the middle of that vector, it jumps back down to the negative Nyquist frequency and climbs back up to 0. This FFT shift pushes all the data around so that the 0 frequency is in the center of this data array. Okay, so, whoops, forgot to do this part. Okay, now we can plot all of our data. So here's the time domain. We can see the claps, regular intervals. This part here is the shouting, and this part here is presumably the high-pitched scream. If we look at the Fourier transform, then we see two enormous peaks at around 6,500 Hertz at negative and positive. And if we zoom up in around positive 6,500 Hertz, we see this big peak here. So this is the horrible screaming noise that we're going to try and eliminate. Okay, so the other way you can look at this data, which is really useful, is to plot a spectrogram. Now, a spectrogram shows how the frequencies change over time. So basically all you're doing is carving up the time data into small pieces and taking the Fourier transform of each of those small pieces. And then you can plot them. So around this time here, we have a clap, and we can see the clap, as you might imagine, is like a delta function. It gives you a burst of lots of frequencies fairly evenly distributed. Then we have silence apart from this enormous screaming noise at 6,500 hertz. This part here corresponds to the person going woo, and so you can see that's the imprint of their voice there. So here you can see how the frequency spectrum changes as a function of time. This is the transform of the whole thing. This is taking transforms along time steps, so you can see how it's varying. The color scale here is in dB, so it's a logarithmic scale. So each time you go up by 20 dB, the amplitude of the sound is increasing by a factor of 100. So you can see this 6,500 hertz part here is really very intense. Okay, so what we need now is a filter to get rid of this. So we're going to do the simplest possible thing. We'll define a vector that is 1 everywhere apart from a range of frequencies around plus or minus 6,500 hertz. So on this graph here, it'll be 1, 1, 1, 1, 1, 1, 1. When we get to this spike here, it'll be 0. And we get over here, it'll be 0, but 1 everywhere else. And the trick I'm going to use to define that vector is I'm going to define a Gaussian function. So I'm using the exponential here. And I'm going to take the an exponential of the frequency data minus 6,500. And if I take the absolute value here, I'll get Gaussian peaks at plus and minus 6,500 hertz. The width of those Gaussian peaks I can change depending on this factor here. And then I can round that. So if it's a number bigger than a half, it'll be rounded to 1, less than a half rounded to 0. And I can subtract all of that from 1. And this will give me a vector that is 1 everywhere apart from around this region here. I'm also adding a tiny little offset here to stop things being completely 0, because that'll make some of the logarithmic plotting a bit unhappy. So that's the filter. And we can define that filter and then apply that filter. Now I'm going to show this on a logarithmic scale here. So the orange is the filter data, and we can see around this frequency here we've filtered everything out. I'm only plotting the positive frequency axis here. The unfiltered data is this blue part here. So we can see we've completely eliminated it. The filter data, however, isn't sort of continuous along here. We can see we've got this big spike going downwards instead of just being a nice sort of smooth spectrum around this area here. And this is the cost you pay for filtering. You're doing it in a dumb kind of way. You can't directly subtract off this signal. We're just going to kill everything around that signal. It's a if you use weed killer, you're going to kill the weeds along with some of the plants that you actually might want to keep. Okay, we can also look at this. I plotted here just for fun the real and imaginary parts of the frequency domain. So the fast Fourier transform. The blue is the real part, and the yellow there is the imaginary part. And we can see if we zoom in, there's an area there which has been filtered to 0. And previously that had an enormous spike on it. Okay, so that's how it looks. Now we can define the Fourier transform in the reverse direction to get back filtered audio data. So this is the input audio multiplied by the filter, and then we do the inverse Fourier transform, IFFT, to get the inverted data. Now, this first plot here, this is the time domain, the real part of the time domain, and we can see claps and shouting, and we've got rid of that big ball of fuzz that we had. If we go back up here, we can see this big ball of fuzz here. So that's the real part. Now, the input data, of course, was all real, but when we do a forward transform, filter, and then reverse transform, we get little numerical errors coming back, and so it's important to remember just to take the real part and plot that. It's also worth checking the imaginary part and making sure that is much, much smaller than the real part. If it's not, something might have gone wrong. So that's why I've plotted here the real part and the imaginary part. We can see the imaginary part spans between minus 40 and plus 40, which sounds like a big number, but it's much, much smaller than the plus or minus 20-something thousand of the real part. So we can basically ignore the imaginary part from now on and just work with the real part. So having checked the imaginary part to make sure it's small enough. If it weren't small, we'd have to go back and look and see if we've messed up the filtering somehow. Okay, now we can play the audio output. And we can hear that the 6,500 Hertz screaming has largely gone away. If you listen carefully, you can still hear some artifacts. And that's because when we've filtered, we've done something fairly dumb. Like I said, you use a weed killer, you kill weeds and the plants around it. And so we've got this, there is an artifact here at that frequency, so we can still hear something going on at that frequency. However, it is much better than the input. If you remember, that sounded terrible. So we've certainly had an impact. We can also plot the spectrogram of the output, and you can see at 6,500 Hertz here, there's still something going on, but it's largely been eliminated, and we can hear the rest of the audio far more clearly.